mixtures of gases. Lots of gas samples are mixtures. Lots of any substances are mixtures. Dry air is a mixture. And the word dry here means not wet. What does wet mean? It's got water in it, right? So wet air would be humid air. Now, the air that we're breathing, even though we live in an arid climate, does have some moisture in it. Even in Phoenix, they have a little bit of moisture in the air. The reason we talk about dry air is because the moisture content of the air varies with temperature and weather and all kinds of other factors, and it's just too complicated. So we talk about dry air. So that's what dry air is. Dry air is a mixture of nitrogen, oxygen, argon, carbon dioxide, and a few other gases. It's mostly nitrogen and oxygen. So that's the air that we're breathing. And this table gives us the composition by volume percent. So volume percent would be the volume of nitrogen divided by the volume of the whole sample of air times 100. And no, you don't need to memorize those numbers. So sometimes we can think of or treat a gas mixture as if it were a single gas. So air is a mixture of gases, but we can treat it as a single gas. We can measure its pressure, its volume, its temperature, just like it was a pure substance. We can even calculate the number of molecules in a sample of air. But the thing is, they're not all the same molecule because it's a mixture. So gases behave independently, and this is something that's somewhat unique to gases. So John Dalton studied mixtures of gases, and we have what's known as John Dalton's law of partial pressures. So what's a partial pressure? Well, an individual gas in a mixture of gases exerts its own pressure. That pressure is part of the pressure exerted by the entire gas. So it's a part pressure, a partial pressure. We could calculate the pressure due to a single gas, and we could call that Pn, where n is the individual gas, by using the ideal gas law. So we have Pb equals nRT. And then if we solve for pressure, divide by volume, volumes cancel out. And so we get the pressure of a gas is equal to the number of moles times R times T divided by V. So if we're looking at gas N in a mixture, it's the number of moles of N times the ideal gas constant times the temperature divided by the volume. Now, in a gas mixture, the temperature of all the gases is the same because it's one sample, right? So all the temperatures are the same, and the volumes are all the same. What's different is the number of moles and the individual pressures that they exert. So Dalton's law of partial pressure says the sum of the partial pressures of the gases in the mixture equals the total pressure. So the total pressure of this mixture is the partial pressure of gas A plus the partial pressure of gas B, etc. You add them up. This is like thinking about a box of fruit, and the mass of the box is equal to the mass of the apples plus the mass of the bananas plus the mass of the oranges, right? So P total is the total pressure. This is Dalton's law. Come on, pointer. Sending request. What request do you need to send? Total pressure, partial pressures of A plus B plus C. So we just looked at the, we can have an equation for the partial pressure of gas N or gas A. That's the moles of A times RT over V, plus the moles of B times RT over V, plus the moles of C times RT over V. And we can factor out the RT over V and have the sum of the moles is times RT over V equals the total pressure. And so we could call the sum of the moles the total number of moles. And so we can say that the total pressure of the gas is equal to the total number of moles times RT over V. we can look at the ratio of the partial pressure of a single gas to the total pressure. And this would be like a pressure percentage, I guess, but not times 100. So if we take the partial pressure of A equals NA times RT over V, the total pressure is the total number of moles times RT over V. And we can cancel out the RT over V, so this is NA over N total. The number of moles of A divided by the total number of moles. The part divided by the whole. So this is a fraction as opposed to a percentage, and it's called the mole fraction because it's moles. And so that is represented in this equation. That funny-looking x is a Greek chi. So chi sub A is equal to the moles of A divided by the total number of moles. So this is a useful equation that we're going to be using. The exam that covers this chapter, there's going to be a whole bunch of different equations on the useful information sheet. So you don't have to worry about remembering the details of what's over what, but you do need to know how to use the equations and remember what the letters stand for. So so this rearranging here, so we've taken P over A, PA over P total is equal to NA over N total. So we can solve this for the partial pressure of gas A. Here, I'll write it out because it's a little hard just to look at it that way. Just multiplying both sides by P total. So the P totals cancel out. So we got P total is NA over N total times the total pressure. So that's what's written right here. And this part, this is the mole fraction. So that's chi A. So the pressure of a gas is proportional to its mole fraction. The mole fraction times the total equals the partial pressure. And this is like percentages, right? If the gas is, if 75% of the molecules are gas A, 75% of the pressure is from gas A. So the partial pressure of any component in a mixture is its mole fraction times the total pressure. Mole fraction is just the percent by volume divided by 100. So when we look at dry air and we see in that table that nitrogen has a 78% composition, we can say its mole fraction is 0.78. This is the percentage, the fraction is just that divided by 100. So if we want the partial pressure of nitrogen at sea level in dry air, the mole fraction is 0.78 times the total pressure. The nitrogen has a pressure of 0.78 atmospheres. I know it's very hard to care about this at 8:15 in the morning. So here's an example problem. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. So this is actually a very tedious problem. We're going to do it anyway. So we've got three numbers in here. It's always a good idea to just pull the numbers out and write them down, because that can help you see what you need to do. So 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton. And it's wanting us to calculate the partial pressure. Well, what do we know about partial pressures? Well, we know that the total pressure, and I'm just going to call it T instead of writing out the word total. In this case would be the partial pressure of helium plus the partial pressure of neon plus the partial pressure of krypton. Right? That's Dalton's law. And we also learned that the partial pressure of any gas in a mixture, we'll just do helium because it's first, is equal to its mole fraction times the total pressure. And then, what the heck was the mole fraction again? The mole fraction of helium is going to equal the moles of helium divided by the total number of moles. Here the total moles is moles of helium plus moles of neon plus moles of krypton. So those are equations I just introduced you to. So if I want the partial pressure of each gas, well, the partial pressure of helium is the mole fraction times the total pressure. Do I know either one of those just without any calculating? What's the total pressure of this gas? 1 atmosphere. How do I know that? At STP. That tells me the temperature of the gas is 0 Celsius, 273 Kelvin, and the pressure is 1 atmosphere. So that's easy to overlook because you don't see any pressure units or numbers. It just says STP. So we know that the total pressure is 1 atmosphere. So the mole fraction of helium times 1 atmosphere. We need the mole fraction. This is the equation for the mole fraction. It's the part we're interested in, the moles of helium, divided by the total number of moles. Do we have enough information to find that? We do. We have to convert grams to moles and then add some moles together and divide. And we just do it. We can do this. So to find the moles of helium, we're going to start with the mass and convert to moles. So we're going to multiply by moles and divide by grams. And here we need the molar mass of helium, which is 4.003. These grams cancel out. 5.5 divided by 4.003. 1.37. And I'm feeling tired and a little bit lazy, and so I'm just going to use the minimum number of significant figures. Just throw caution to the wind. Live dangerously this morning. I did this yesterday and it worked out fine. It's not too scary. So for neon, I'm going to do the same process. I need to convert grams into moles. So I look at the molar mass of neon, 20.18. That's a sad 8. There we go. 15 divided by 20.18, 0.743 moles. And the moles of krypton is the mass of krypton times moles over grams. We need the molar mass of krypton, which is 83.80. 35 divided by 83.8. 0.408 moles. Did I screw something up? 83 grams. Yeah, I divided by 85. Thank you. That's why it's always a good idea to do the math twice. So it should be 4.18. There. Thanks for catching that. So, those individual steps aren't hard. but there's so many things we have to do here. It's easy to get lost, right, and forget what we're doing next. We're trying to find the mole fraction of helium, and then we're going to need the mole fraction of the other gases as well. So we've got moles of helium. I need the total number of moles. So the total number of moles, N total, is going to be the sum of those. 1.37 plus 0.743 plus 0.418. 2.531 moles. Okay, so now I can calculate mole fractions. So the mole fraction of neon. So, no, not neon, helium. They look so much alike. Helium, so we're going to have the moles of helium divided by the total number of moles. 2.531. And the moles cancel out. So 1.37 divided by 2.531, 0.541. There's no units on a fraction. There's no units on a percentage other than percent. So that's the mole fraction. I can calculate the mole fraction for the neon in a similar way. Here it's the moles of neon divided by the total number of moles. Moles cancel out again. This is very much like calculating a percentage, but we're using numbers of moles instead of masses or volumes or something. So this is 0.294. And then for krypton, .165. What should be true of the what relationship is there with all those mole fractions? They should all add up to 1. Just like if you have percentages, they should add up to 100, right? And if you check this, they do. Now, sometimes if you check that, they'll be off by a smidge in that last uncertain digit, and then we say that's okay. But this time it came out perfect. I'm not sure why. Okay, so here's my mole fraction. To calculate the pressure, I take the mole fraction times 1. So this is super challenging, right? Get out your heavy-duty calculators. 0.541 times 1 atmosphere. I think that's 0.541 atmospheres. I know. That's the pressure, partial pressure. Pressure, percent, both start with P, so, and then there's partial, and that starts with P also. So that's the pressure for the xenon. For the neon, not xenon, this is helium. For the neon, times 1 atmosphere, and we get 0.294 atmospheres. And for the krypton, multiplied by 1 atmosphere, and we get 0.165 atmospheres. Those partial pressures should add up to the total pressure. So there's one answer. This has 3 answers. And there's another one. And the other one's up here. Any questions? Yeah. Pardon me? If it says STP, then the pressure would be 1 atmosphere. And if it isn't, they have to tell you what it is. Because you can't calculate the partial pressures without knowing what the total pressure is. Any other questions? Here's a conceptual problem. Gas mixture contains an equal number of moles of helium and neon. The total pressure is 3 atmospheres. What are the partial pressures of each of the gases? So if they have equal numbers of moles, now we're not accustomed to thinking of fractions. What would the percent of helium be? 50%. And the percent of neon would be 50%, because they're equal, right? So then their mole fractions are 0.5 and 0.5. And if their mole fractions are equal, then what are their partial pressures? Also equal, right? So what's the answer? C. Any questions about that? Another example. Sample of hydrogen gas is mixed with water vapor. The word vapor and the word gas, same thing. Just water gas sounds funny, so we say water vapor. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Just so much stuff. Pull the numbers out, write them down. 755 torr. And I've got 24 torr. That rhymes. And I've got 1.55 liters, and I have 298 Kelvin. Well, I know that 298 Kelvin is a temperature, so I'm going to call that T. And 1.55 liters is volume, so I'm going to call that V. Okay. Now, these other two things are both pressures, and it says pressure for both of them. So this is a pressure, and this is a pressure, but they're different pressures, right? So the first one is the total pressure. So I'm going to call that P sub T for total. And then this is a partial pressure for water. So I'm going to call that pH2O, the partial pressure of water. Bless you. So I labeled all the stuff I was given, and now I want to look at where am I trying to go with all of this? What's the question? How many moles of hydrogen gas? Moles of hydrogen gas is what we're trying to find. So here we have a gas mixture. There's hydrogen and water. We could find the total number of moles of gas, but we want the moles of just the hydrogen. So we need to use the pressure of just the hydrogen. The total pressure is equal to the sum of the pressures of the individual gases. So we've got hydrogen that we're looking at, that we want to find out about, hydrogen plus water, and these have to equal the total pressure.
Why is it hydrogen plus water? Hydrogen plus solids?
Well, I have hydrogen gas and water. Yeah. So this kind of math is so simple that it becomes difficult. How do I find the partial pressure of H2? It's the total minus the other one, right? P total minus pH2O. Well, they gave me P total and pH2O. So P total is 755, pH2O is 24. I subtract those, I get 731. Not forgetting my unit is torr. Okay. I now have pressure for the hydrogen. I have the volume and the temperature. Can I find the number of moles? Yeah, I just need the ideal gas law. We've rearranged this to solve for moles before, so I'm not going to go over that again. But the number of moles is P times V over R times T. And we've got the ideal gas constant in here, and so that dictates what the units have to be. Has to be atmospheres, liters, moles, and Kelvin. I've got Kelvin and liters, but my pressure is in torr, so I need to convert that to atmospheres. 1 atm over 760 torr. (731) divided by 760. 0.96184 atmospheres. So I've got all the numbers I need. I'm going to put them into my equation. 0.96124. That's an 184. Atmospheres. Always, always, always write the units. 1.55 liters divided by 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature is 298 Kelvin. Check your units. Atmospheres cancel, liters cancel, Kelvins cancel. End up with 1 over mole, which is the same as mole. And be careful when you put this into your calculator. So get it out and do it and make sure that it's cooperating with you. .0610 moles. I get a lot of questions when students see a small number of moles. Is that okay? Well, we couldn't have that many atoms, but we can have that many moles. Because can you have half a dozen? Yeah, you can have half a dozen. That's 6 instead of 12. The mole is a much, much bigger number. And so you can have a very small number of moles and you haven't gotten down to an individual atom yet. Anybody have any questions? If you're getting a different answer, it's probably much larger and you are accidentally multiplying the whole thing by 298 instead of dividing. So watch that. 0.0610 moles. We're going to talk about deep sea diving. Kind of circling back to the beginning of the chapter. So, diving down under the surface of the water, the pressure increases dramatically because water is more dense. And in order to be able to breathe, you have to be breathing pressurized air. Well, breathing pressurized air, you get a higher partial pressure of oxygen because the total pressure is higher, right? And so this can lead to elevated concentrations of oxygen in your tissue. And you might think, well, oxygen is good for you. More oxygen is better, right? No. Everything is toxic at some level. Water and oxygen are both necessary for life, but will also kill you if you get too much. So there's really nothing that is completely safe, right? So oxygen toxicity at pretty high partial pressures above 1.4 atmospheres. We don't have to worry about that happening as we wander around Fresno. It's not going to happen by accident. It's called oxygen toxicity. Hypoxia is the opposite. Hypo is that prefix that means less than, right? So it's less oxygen, oxygen starvation. So that occurs when oxygen pressures are too low. That can happen if you fly in an airplane that isn't pressurized, or you go up into the mountains and you start to get out of breath with a little bit of exercise, because the atmospheric pressure is less, and so the partial pressure of oxygen is less as well. And this is what it is at sea level. This is what we're accustomed to. And we get into this yellow zone at only a little bit less than what we're used to. There's this big region up here that's safe for higher oxygen. But still, too much oxygen, not good. When you're breathing compressed air, you're getting too much oxygen, you're also getting too much nitrogen. And obviously that's not good for you either. That leads to nitrogen narcosis, sometimes called rapture of the deep. And I'm told that's similar to being drunk, alcohol intoxication. So you might think, well, what's so bad about that? I kind of like that feeling maybe. Personally, I don't. But, well, would it be wise to be drunk when you're 30 meters below the surface of the water? Probably not, right? So not a good idea. So how do we get around this? Well, let's look at this picture first. So up at the surface, the pressure is 1 atmosphere. So you're getting a partial pressure, 0.78 atmospheres of nitrogen and 0.21 atmospheres of oxygen. That's ideal. Down here, 30 meters below, in order to breathe, the pressure has to be 4 atmospheres. Now you're getting 3.12 atmospheres of nitrogen and 0.84 atmospheres of oxygen. So these levels are too high. You can't reduce the pressure, but you can change the composition of the air, the gas that you're breathing. So one of the mixtures that divers use is called heliox. It's a mixture of helium and oxygen. And so because there's no nitrogen in it, you're not going to get nitrogen narcosis by breathing heliox. Now, could you still get oxygen toxicity? You could if you don't manage the pressures and the mixtures of the gases correctly. Do you have any comments?
Oh, I just remember
Yeah.
we were making our own oxygen.
Yeah.
And I was on there, and one of our cords was back in the boat. I was mad. One of my other guys, that's back there, irritated. Next thing I know, I was happy. I just got nailed with oxygen, pure oxygen. So yeah, it took a while to come down off the
Yeah. Yeah, so, some of these things that are bad for us can feel good at the time, but yeah, that's interesting. Okay, so let's get back to boring calculations. A diver breathes a heliox mixture with an oxygen mole fraction of 0.050. No units because it's a fraction. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? This one is way simpler than the last one. But let's write it down. So we've got 0.050, and that's the mole fraction for oxygen. So that's big funny X, chi O2. Or if you can't remember that, you could just write mole fraction of oxygen. And then we've got 0.21 atmospheres, and that's the partial pressure of oxygen. So that's PO2. And then the question is, what's the total pressure? So that's PT. P total equals what? Well, there was an equation that related these three things. So the partial pressure of oxygen is equal to its mole fraction times the total pressure. So they gave us two of the quantities we need to solve for the third. All we have to do is rearrange the equation. I want to get P total by itself, so I'm going to divide by the mole fraction of oxygen. So those cancel out. So the total pressure is going to equal the desired partial pressure, 0.21 atmospheres, divided by the mole fraction. 4.2. Any questions? What happens when you breathe helium? Your voice gets all high and you sound like Mickey Mouse. So if you're diving and you're breathing heliox, that's going to happen to your voice. But the thing is, you're underwater, nobody can hear you talking, so yeah, no benefit there. Yeah, wasted. Perfectly good waste of helium. 4.2 atmospheres. So we can make gases by chemical reactions, gas evolution reactions. And then if we want to collect the gas, that's a little more involved than just, say, collecting a liquid or filtering out a solid product. So we often collect gases by having them displace water from a container. So we can set this up. It looks something like a mercury barometer, but it's got water in it instead. So some tall container often will use like an inverted graduated cylinder or something, full of water, inverted into a dish of water. And at the beginning, this is completely full of water. Here we have our reaction occurring in a test tube, and we've got a stopper and a tube leading from the stopper so that as the gas is formed, the only place it can go is through here, and it comes in under this container. The gas will float, it'll go up, and so it'll get trapped. And as it goes up, it's going to displace the water. So in this space here, we have the gas that we've generated, but we also have water vapor because water evaporates, right? So here we have water, and the water is evaporating into this space, and so we're going to have hydrogen plus the water vapor. But as we just learned, calculating the partial pressures there and the moles is not really all that difficult. The partial pressure of the water vapor is typically called the vapor pressure. And the cool thing about this is it only depends on the temperature. So if you measure the temperature of the water, you can assume that the gas is the same temperature as the water. They're right next to each other. And you don't have to actually measure how much water is in that gas. You can just look it up in a table. So we have tables available like this. This one only gives every 5 degrees. You can look up ones that are much more detailed, but this will show you at 20 degrees Celsius, the vapor pressure of water is 17.55 millimeters of mercury. So if we know the temperature, we can just go look up the vapor pressure of water, and then we subtract that from the total pressure, and we've got the pressure of the gas we're interested in. So let's do an example. A sample of acetylene, C2H2, is collected over water. The total gas pressure is 738 torr, and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? Again, pull out the numbers. 738 torr. And 523 milliliters. 23 degrees Celsius. 21 torr. So let's identify what these things are. This says the total gas pressure is. So I'm going to label that P total, PT for P total. This is the volume. This is the temperature. And this other one is the partial pressure of water, the vapor pressure of the water. What I'm trying to find is grams of acetylene. These units that I'm seeing over here should remind us of what equation? The ideal gas law, PV equals nRT. That allows us to find the moles of gas, right? If I have the moles of acetylene, can I find the grams? Yeah, I could do that. So to find the moles of acetylene, I need the pressure of the acetylene. I don't want the total pressure. So the pressure of the highlighter doesn't make a good pen. The pressure of the acetylene is going to be the total pressure minus the partial pressure of the water. So that's what, 717 torr? Is that going to be a good unit for the ideal gas law? No. Let's just fix it up now. Convert that to atmospheres. Torrs cancel out. Zero 0.943 42 atmospheres. Is milliliter a good unit? No, we've got to convert that to liters. We are short on time, and I've already done that many times. There's the volume in liters, and then the temperature, we're going to add 273, and we're going to get 296 Kelvin. So N equals PV over RT. So it's the pressure, atmospheres, times the volume, 0.523 liters, divided by R, and the temperature. Again, we can check that the units cancel out. So the moles is the pressure times 0.523 divided by 0.08206 divided by 296, 0.0203 moles. And then I want grams, so I'm multiplying by grams, dividing by moles. Do you see how many times we convert units in this class? It's like all the time. So I need the molar mass of acetylene, 2 times 12.01 plus 2 times 1.008. 26.036. So 1 mole of acetylene weighs 26.036 grams. .020313 times 26.036, 0.537 grams. Any questions? I guess I didn't give an answer for that one. That was because that was like an extra example. Here's another one. Common way to make hydrogen gas in the laboratory is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. Suppose the student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen in milligrams does the student collect? So I read all the words, and I'm going to pull out the numbers got 154.4 milliliters, and I've got 742 millimeters of mercury and 25 degrees Celsius. Well, 25 degrees is the temperature, and 154.4 is the volume, and this pressure is the total pressure. So this one is not as obvious, but we've got the keywords there: collected over water. So I don't just have the gas I'm interested in, I have the gas I'm interested in plus water. And the total pressure is what is measured, and then I have to figure out what the partial pressure is to find the moles of just hydrogen. They didn't give me the partial pressure of water. I have to go look it up. You don't memorize those things, but you do have to go look them up sometimes. So over here, it was 25 degrees, right?
Yeah.
So I'm going to look at this table, and I'm going to see for 25 degrees Celsius, the pressure for the water is 23.78 millimeters of mercury. So, again with that, 23.78 millimeters of mercury. So if I'm trying to find the mass of hydrogen, I need the pressure of just the hydrogen. So I have to subtract the water from the total pressure. So pressure of the hydrogen is equal to the total pressure, 742, minus the partial pressure, and I do think it's better to subtract before you convert to atmospheres. So this is giving me 718.22 millimeters of mercury. I've got volume, I've got temperature, I can use the ideal gas law. I'm going to calculate the moles, and then I have to convert to grams and then to milligrams. N equals PV. Well, let's fix those units first. 154 milliliters is 0.1544 liters. And 25 degrees Celsius is 298 Kelvin. So the moles of hydrogen is the pressure of the hydrogen. Nope, didn't fix that one yet. So millimeters I need to convert to atmospheres. It's very easy to copy down numbers incorrectly, and I see that happening in some of your lab reports. And while it is understandable, it also gives you the wrong number. And there are lots of situations where it doesn't matter how well intentioned you were. If you give them the wrong number, something bad is going to happen. Okay, so then we can do the calculation. I'm getting a small number. I've got 3 significant figures, so 59668. And that's moles of hydrogen. So now I convert my moles to grams, molar mass of hydrogen, 2 times 1.008. So moles cancel out. And then it wants milligrams. So multiply by milligrams, divide by grams, so those units cancel out. Milli stands for 10 to the minus 3. I have 1 milli on top, and I have 1 10 to the minus 3 on the bottom. So 11.9. milligrams of hydrogen. Questions? Yeah. Am I showing you the hardest ones? That's an excellent question. I'm trying to show you a variety. So some of them are really simple, and some of them, like this, is more involved. And then on the exam, there's going to be at least one problem, probably 2 or 3, that are different than anything we saw in lecture. But they require the same pieces that we learned and used in other things, but you have to put the pieces together in a different way than you've done before. Yeah?
Getting 12 points.
You keep getting 12 something?
Yeah.
Well, I could have screwed up. Did you get the same number of moles that I got? No?
But even like doing the calculation you have before, I'm getting 12.
Well, let's check that because I've already screwed up once this morning. I've got at least 2 more times coming today.
No, I put that calculation in my calculator.
Yeah. Now I'm getting 12.1. What did I do before? I multiplied by 2.0016 in my calculator. Thank you for catching that. Any other questions? There's just so many ways to mess it up, right? So many ways, yes.
So when you were talking about the test, how it's going to be different, it's
Mhm.
just really like you're taking the ideal gas law and just like moving it around different ways is what you mean.
So yeah, rearranging the ideal gas law, also incorporating things like unit conversions, milligrams to grams, partial pressures, subtracting from total pressure, converting from moles to grams. You could have density showing up in there. It's a little bit like, let's see, what would be a good analogy? Can't think of one. Usually they just come to me. But I'm giving you lots of different pieces, and I'm asking you to put them together in a new way. Yeah.
Yeah, they're going to be like a lot of questions on the test, because like if one question takes like 5 to 10 minutes and we have like 50 questions, that's a lot of time.
So most of the questions on the exam will take probably less than a minute. There's a bunch that are just basically knowledge, where it's like, well, you either know it or you don't. So there's no point in thinking about it for too long. There are some that should be very quick calculations. There will be a couple that are very involved, but then I'm also giving you like 2.5 hours to do the exam. So time shouldn't be an issue. Yeah.
Do you know if they've gotten the schedule too?
I don't.
They did?
They did? They did? Awesome.
They got
Such a disaster, that bookstore. Okay, on to other things. So, yeah, 12. So